Hey there, welcome back to the Energy Blueprint podcast. I'm Ari Witten, your host, and I'm here today with Dr. Lee No, who is the author of this book, which I got several years ago, which I am a huge fan of. And I've wanted to interview him on the podcast for a very long time because I'm truly a fan of his work. And he's also about to publish the updated version of this book, which is called Mitochondria and the Future of Medicine, which is coming out next month in February. Or maybe this month when I publish this podcast might be in February. So it might be right around the time I publish this. Maybe we'll publish this right as the book's coming out, actually. So without any further ado, basically Dr. Lee No is an author, is a naturopathic doctor, and has had various roles as a research specialist. And what else? Let me see. What am I missing here? You know, there's a whole bunch of titles. You've been a medical advisor, a scientific evaluator, a director of research, and research of development for major organizations. So welcome, Dr. Lee No.
Thank you. My pleasure, Ari.
Yeah. So mitochondria.
Yes.
Mitochondria are a very, very big deal. And, you know, I was just telling you before we started this podcast that reading your book several years ago was actually a big deal for me, because at the time I was just starting to have an inkling of the importance of mitochondria and that whole connection of mitochondria and fatigue specifically. And it was really reading your book that really solidified that for me and solidified, whoa, this is a really big deal in fatigue. And almost nobody's talking about this. Everybody's still really hung up in the adrenal fatigue model of things and kind of talking about things through the lens of adrenal function and cortisol. And here you were presenting this whole other understanding of fatigue and this whole other layer of dysfunction that nobody's really talking about and nobody seems to understand very well. So thank you for that. And I, you know, as I was telling you before, I'm truly a fan of your work. So I highly, highly recommend everyone pick up your new book when it's published. So with all that in mind, let's start with the basics. What are mitochondria and why do they matter?
Yeah, so, you know, and this is one of the things that is becoming more clear as research continues, is that what we learned about mitochondria as way back in high school biology as a powerhouse of the cell, well, and that continues to be true, but we're seeing that it's far more important than just the way that it was presented to us in high school. And essentially what, just to kind of bring everyone back to the beginning, just so that we're all on the same page, mitochondria is one particular organelle in the cell. So when you look at, you can think of organelles almost like organs are to our body. What they're basically special or defined structures that carry out specialized functions. So, you know, just like the liver carries out a specialized function in our body, the heart, the brain. Well, the cell has these organelles, and the mitochondria is just one of them. And what its specialized function is predominantly energy production. But where it becomes really important is that when you look at everything that happens in a cell, and I mean literally everything, you know, from the copying of DNA, the transport of ions from one part of the cell to the other, the maintenance of the cytoskeleton that maintains cell shape. Everything that happens in the cell requires energy, and it's the mitochondria that is responsible for producing over 90% of that particular of that cell's energy needs. So when you don't have energy, everything starts to fall apart. And that's one of the reasons why mitochondria is so critically important to life in general.
Yeah, absolutely. So how many, you know, this is one component in our cells. Do all cells have mitochondria, and how many mitochondria do they have?
Yeah, so in general, you can think every cell or most cells do have mitochondria, and the number of mitochondria in any given cell is really dependent on the energetic demands of that particular cell. So if you have a cell that doesn't really have that great of an energy demand, like red blood cells as an example, they might have a few, if any. But when you start to look at more metabolically active cells or tissues, such as the heart and the brain, we're looking at a couple thousand mitochondria per cell. And that really is just an illustration as to the energy demands, because of course, the more mitochondria you have, the more energy you're able to produce.
Yeah. Now, I know that there's a very complex but also very fascinating story of kind of how mitochondria evolved based on evolutionary biology. And I know we kind of got to stay surface level because that's probably a whole several-hour conversation unto itself.
Right. Yeah.
I want to spend the majority of our time here focused on sort of more practical things for maybe people suffering from fatigue. But can you talk a little bit about kind of the origins of mitochondria from an evolutionary biology perspective, and why they have their own DNA, why they sort of this peculiar thing of mitochondria having their own unique DNA separate from our DNA?
Yeah. So when you look at, you say, 2 billion years ago, the Earth was just a mass. Anything that we could refer to as life was essentially just bacteria. So everything that we see with our visibly with our own eyes, without a microscope, that's living in the planet today, didn't exist 2 billion years ago. It was just bacteria. And what ended up happening was, at one point, one bacteria engulfed another bacteria. And normally when that happened, the bacteria ended up getting digested. But at a certain point in evolution, in history, what ended up happening is, instead of that bacteria being digested, it created a symbiotic relationship with that host. And what ended up happening over the course of a few million years after that is this slow evolution where that engulfed bacteria then became specialized in energy production. And to make the long story short, that energy production is what allowed eukaryotic cells or multicellular organisms to thrive and grow.
Mm-hmm. Yeah, and it's funny, as you were talking just now, I was reminded of when I was a teenager. I was really fascinated with marine biology, and specifically coral reef aquariums. And one sort of interesting fact of live corals is they actually have another living creature inside of their cells, and that's actually an algae. I'm talking about most corals. They have an algae called zooxanthellae, and it's basically a photosynthetic algae that lives inside of the cells of the coral itself and harnesses the energy of the sun and produces energy. And that is sort of, it's funny, I'd never really connected that before, but it's a similar relationship of kind of having this other little creature living inside of your cells producing energy that the host benefits from. So anyway, let's talk about free radicals and aging. This is a fascinating subject, and you talked about it at length in your book. And this is a subject where there's a lot of misconceptions. So yeah. we have, common ideas around this is we have free radicals are bad and antioxidants are good, and free radicals damage our bodies and we need antioxidants to neutralize these. So free radicals bad, antioxidants good. That's the way that most people are taught to think about this. But I know that the story is quite a bit more complex than that. So can you talk a bit about that?
Yes, absolutely. And this is where, I think it's an important discussion to have, because the nutritional supplement industry, as an example, really push antioxidants. And what we're starting to realize is that might not actually be a good thing in all situations. And that's because when you look at the cell, and I know free radicals have often been presented as a negative thing, and for the most part they are. But free radicals also have an incredibly important signaling role. And what ends up happening is, if you quench those free radicals, the cell just doesn't work properly. So what ends up happening is, in certain situations, and keep in mind, just like any conversation, when we say something, it has to be taken into context of the greater conversation for us to really understand what's going on. And that is the same thing with free radicals. So even though we think of free radicals in general as a bad thing, when you look at the overall context of what's happening in the cell, in certain situations, those free radicals actually allow our bodies to adapt and become stronger. So without those free radicals, our cells would actually slowly deteriorate over time. And what's really interesting is that I think a couple of years ago there was a study, and I think it was on worms. And forgive me for not remembering the details of this study, but what it actually showed was that oxidative stress in this particular species of worms actually extended lifespan. So it's really interesting to understand, for a very long time, we thought free radicals as only having a negative impact to your health. But like I said, under the right context, these free radicals are extremely valuable, and we need to kind of understand how we can leverage that to make our body stronger.
Yeah, and on that point, there's also a number of lines of research in humans as well that have found that antioxidant supplementation does not extend lifespan. That one of the basic tenets of kind of the free radical theory of aging was that free radicals are bad, antioxidants are good because they neutralize them and therefore prevent that cell damage, prevent it from aging us. And so we had, for many decades, we had all these theories that it was going to prevent all kinds of diseases, heart disease, cancer, diabetes, and extend our lifespan by stopping that free radical induced damage. And there have now been dozens of studies on this in humans, and they've reliably and consistently shown that antioxidant supplementation does not prevent these diseases and does not extend lifespan.
Absolutely. And in some cases can actually do more harm than good.
Yeah. I mean, there's that's actually what I said was being a little generous, because like you said, there's a few studies that have found increased risk of certain cancers and things of that nature.
Yeah. Now, mind you, to be fair, I think it's important to also understand that in certain situations, those compounds that we typically think of as antioxidants do have benefit and have been shown to have benefit and improve the health of individuals with a particular health condition. But when you're looking at an overall healthy individual looking for prevention and even vitality and longevity, that's where the free radical theory of aging and health kind of starts to fall apart.
Right. Yeah. So vitamin E serves important roles. Vitamin A serves important roles. Vitamin C, scurvy is obviously a bad thing. Overt vitamin C deficiency is a real thing. But in people who are otherwise vitamin C sufficient, for example, supplementing with more doesn't seem to have any benefit.
Right. Exactly.
So, so how does this work? So if this is not what's going on, if free radicals, this whole free radical theory of aging isn't as simple as we thought, that free radicals are bad and are causing disease and aging us, how does this actually work on a cellular level? What's going on?
Yeah. So what we thought, and this kind of, and I didn't answer your question about the mitochondria having its own DNA, but remember, because mitochondria are descendants of bacteria, they've retained their own set of DNA. And the difference between the DNA in mitochondria and the DNA in our nucleus is that the DNA in the mitochondria are in the immediate proximity to where those free radicals are generated in our mitochondria. And keep in mind that our mitochondria is the #1 source of endogenous free radical generation. So those free radicals that are generated within our body, the vast majority are produced in the mitochondria, and that DNA resides in the immediate proximity of where those free radicals are generated. The other thing to keep in mind is that this DNA is relatively unprotected. So when you look at the DNA in the nucleus, it's protected by these elaborate proteins called histones, and those are absent in the DNA in the mitochondria. And the other thing to keep in mind is that there is very little what we call junk DNA in the mitochondria. So whereas in the nucleus we have apparently reams and reams of all sorts of DNA that don't code for genes, so we term them junk DNA. In the mitochondria, that DNA is so tightly packed that if there's free radical damage at any point to that DNA, it's likely going to have a negative impact to the gene that it codes for. So one of the things that we're starting to see is that as free radicals are generated, it's not so much that the free radicals themselves is bad, but the damage that they do to the mitochondrial DNA. And when that mitochondrial DNA is damaged, it can no longer code for certain proteins, and the overall function of the mitochondria and its energy-making capacity start to decrease. And going back to what we said earlier on, everything that happens in the cell requires energy. So you start to damage the DNA that's responsible for producing that energy, everything's going to start to fall apart. And that is what now is seen as the predominant theory for aging, is what we call the mitochondrial theory of aging. So it's not so much the free radical theory of aging or the wear and tear theory of aging. It really is being shown that mitochondria and the ability of that mitochondria to function optimally is what is the main gauge of longevity and health in our bodies.
Yeah, beautifully explained. So I want to go back to one thing you said that might not be easily understandable by some people who maybe haven't done much reading in this area. But think of like a mitochondria, like as a little sac inside of the bigger sac of the cell. And there's kind of free radicals and oxidants going on outside of the mitochondria in the greater cellular environment. So free radicals, like let's say from smoking or from, I don't know, various toxins in the environment and things like that. And then we have a whole set of antioxidants, dietary antioxidants, as well as our own body supply of production of all kinds of different antioxidants. And there's sort of a battle going on there in that extracellular environment of antioxidants and oxidants. And then within the mitochondria itself, there's also free radicals being produced by the mitochondria inside of the mitochondria that are then basically getting, flung off and like sparks from a machine or something, and then reacting with the DNA inside of the mitochondria. Yeah. So please correct me if I've explained that in a bad way, but I just want people to get that there's kind of the cellular stuff that's going on in the cellular level and then within the mitochondria.
Yes, absolutely. And going back to our discussion around antioxidants, those dietary antioxidants that we ingest have a much larger impact to the free radicals at the, in the extracellular matrix, as an example, or at the cell membrane. But it's very difficult, if not impossible, for the vast majority of those dietary antioxidants to actually reach those free radicals being generated within the mitochondria. So you're absolutely right in explaining the two different battles that are going on. One more in the periphery, and then one more centrally within the mitochondria. And that's an excellent way to explain it.
So it's what you're saying is it's specifically the free radicals and the oxidative damage that's happening inside of the mitochondria, largely being produced by the mitochondria, that are damaging mitochondrial DNA. That's specifically the main thing linked with aging. Is that correct?
Absolutely. Yes. Yeah.
Okay.
Exactly.
So if not sort of the story of dietary antioxidants and the typical way that people think about this, what are actually responsible for causing the increased rate of aging, like the increased amount of free radical production at the mitochondrial level?
Yeah. So first, there are a number of different things that do have a negative impact to the mitochondria. And I'll start with the things that are, I guess, more easily avoidable. And so things, what we would call mitochondrial toxins, and things like a number of different pharmaceutical drugs, for example, have a negative impact to the mitochondria. So one of the main ones would be statin medication. So statins are a class of drugs that I think it's the #1 prescribed class of drugs in the world, and its purpose is to lower cholesterol. So when you inhibit the production of cholesterol within our body, we can lower cholesterol. But the thing is that same pathway is also responsible for producing another critical component of the within the mitochondria called coenzyme Q10. So when you stop producing that, you're missing a key component. So when it ends up happening is you start generating free radicals within the mitochondria. So that goes on to inflict damage. Another big class of drugs are antibiotics. So going back to the fact that mitochondria are used to be bacteria, antibiotics have a particularly harmful impact to mitochondria. The other thing to keep in mind is that there are many different external toxins that do reach the level of the mitochondria and have a negative impact. So I know a number of different pesticides have been shown to have a negative impact to the mitochondria. Certain artificial colors as an example. But on more of a day-to-day basis, and probably what's more relevant to our conversation here, is a mismatch in supply versus demand. So one of the things that you have to keep in mind, and I believe you talk about this at length in a number of your videos, is that when you have too many calories coming in, which is those calories supply electrons, and those electrons eventually can go on to make energy or free radicals. And then the other side of that equation is demand. So if you don't have enough demand for that supply, that's when all those electrons are going to spill out and create free radicals, as opposed to produce energy. So the two big examples, and this is a generalization I should add, is if you're consuming way too many calories for your activity level. So it doesn't necessarily mean, that you. So sorry. Let me finish that train of thought. So if you have too many calories and you're not using up those electrons, that's when they're going to spill out and cause free radicals. The other side, or the other example is if you're sedentary. So you're not using up that energy that's produced. So even if you're eating a fairly moderate amount, so you're not necessarily overeating, and you might be eating rather healthy as well. But if you're not physically active, you're not using up that energy, and those electrons, those calories coming in, will spill and create free radicals. And one of the reasons why you really want to make sure that you're not just looking at the calories consumed, but you're also looking at the other end of the equation, the demand. And that is where you can really start to moderate or minimize the free radicals that are generated within the mitochondria.
Mm-hmm. So, based on that, and I know that's just one example of many, but based on that, it would seem that calorie overconsumption and fat gain in general, which is sort of indirectly tied to this, is almost directly linked with accelerated aging.
Absolutely, yeah. A number of studies have shown that, and not only accelerated aging, but pretty much all age-related degenerative diseases have been linked in one way or another back to excessive calorie consumption. So it's incredibly important to, like I said, match supply to demand.
Mm-hmm. So what's actually going on a mitochondrial level that's causing this? So the food creates all these electrons, and then what's going on with those electrons in the state of sort of energy excess or mismatch between supply and demand that translates them into free radical damage on mitochondrial DNA?
Okay, so, and I hope I'm not going to get too technical here, but the way energy is produced, it happens in a number of different stages within the cell. So the first stage is glycolysis, which happens actually in the cytosol, so not within the mitochondria. And then the end products of glycolysis make their way into the mitochondria. It participates in the next stage, which is many people might have learned it as a Krebs cycle. I think that term has kind of fallen out of favor. I call it the tricarboxylic acid cycle. And out of that cycle comes other energy molecules that enter what we call the electron transport chain. And this is where the electrons from all the food that we consume get transferred. So the electrons then go into the electron transport chain. And as long as it's flowing down the chain without any, speed bumps or roadblocks, everything's cool. But in some situations, what we see is that at one point or another, there's a roadblock, and what ends up happening is that those electrons can no longer go any further. And just in my book, I use the analogy of a train and a train station. Basically, all these complexes within the electron transport chain can hold one electron, so to speak. And it can't accept another electron until that electron is passed off to the next complex in the chain. So in a situation, as an example, where we consume far too many calories and we don't have enough complexes to continue to push those electrons down the chain, there's a backlog, and the next train entering the station, what we're going to have is a collision, and that is essentially where those free radicals start to spill out of the electron transport chain and cause free radical damage to the mitochondrial DNA that's right within its proximity.
Mm-hmm. I'm debating where to go from here next. So there's a couple options. One, I know that's tied to what you just explained is NAD+, and that's a really kind of hot topic right now. Mm-hmm. So we could either go there, or the other option is that I'm thinking is to just talk about why mitochondrial damage is tied to so many different degenerative diseases and fatigue in particular. I'll let you choose.
Yeah. Okay. So I think we might have time to touch upon on both of them. I mean, depending on how deep you want to go with each particular topic, but yeah, NAD is really an interesting area of focus because what we're NAD plus is one of those energy molecules that comes out of the tricarboxylic acid cycle, or the TCA cycle I mentioned. And what we're seeing is that that ends up getting turned into something called NADH. So the balance between NAD plus and NADH has an important role in this cell. And what we're seeing is that if you have too much NADH and not enough NAD plus, that ratio is upset, and all sorts of different things can start to fall apart. And again, this in a simplified way, we can look at it as, you know, a backup of electrons again. But I think it goes far deeper than that in terms of gene activation. NAD plus, for example, can activate certain genes called sirtuins, which are linked to life extension and longevity. Things like glucose control, metabolism in general. So there are a lot of different areas of study that are going on right now that's really focused around NAD plus biology. So really cool stuff going on. And it's also important to know that there are important nutrients that support the function of NAD plus and normalizing that ratio as well.
Mm-hmm. Yeah, and just to emphasize that a bit more, there's literally communication going on from this ratio of NAD plus and NADH. There seems to be I've read some research on communication from the mitochondria to the nucleus, dictating gene expression, the expression of genes related to, as you said, inflammation and the protective factors for mitochondrial health and so on. It's influencing all sorts of different genes, whether they switch on or off, that we know are linked with longevity and disease prevention.
Right, exactly. Not only is it absolutely true what you just said, but when we kind of zoom out a little further, that interplay between the mitochondria and the nuclear genes has been shown to have so many different impacts to the viability of the cell and the ability of the cell to carry out its function. So not just gene expression, but so many other things as well.
Mm-hmm. So let's see. Let's get into some specific diseases, and maybe we should, with the amount of time we have left, I'm thinking let's talk about fatigue. How are mitochondria related to fatigue?
All right, so that's a pretty simple explanation, because of course fatigue is really a lack of energy, and considering that the mitochondria is producing over 90% of the energy in our bodies, of course, if you're not able to produce enough energy, you're going to experience that on the macro level as fatigue. As you mentioned, there is a lot of research going on that look at mitochondria as being the core of fatigue and chronic fatigue. And that's not to discount what's going on with the adrenals or the thyroid. What's going on in those situations is still absolutely true, but if you dig deeper, the root is mitochondrial dysfunction. Mm-hmm. So there is this interplay between, the mitochondria and the adrenals and the thyroid. But it's always when you ask why. So as an example, you ask, why are the adrenals fatigued? Why are they not able to produce the hormones that it's responsible for producing? And you keep asking why, you're going to get down to the cellular level and the organelle level, and you're going to start to realize that it's dysfunctional mitochondria. Everything that happens in the cell, again, requires energy. And one of the things that I mentioned, the brain and the heart earlier, but organs in general have a very high metabolic demand, and these organs are producing hormones, packaging them up, secreting them, and that all takes a lot of energy. So if your adrenals cannot have the energy it needs to produce those hormones and make your body's metabolism where it needs to be, again, you're going to experience that as fatigue.
Mm-hmm. So Why then, let's say mitochondrial dysfunction is the core of chronic fatigue. Why can't we just take like a bunch of supplements, take a bunch of D-ribose and alpha-lipoic acid and acetyl-L-carnitine and CoQ10 and so on, and then a week later everything's fixed?
Yeah, so especially when it comes to chronic fatigue, these individuals are typically suffering from long-standing a long-standing condition. And what ends up happening is that it's not only do you need a long time to kind of recover that, but what ends up happening is during the time that your body is starting to kind of go into the phase of chronic fatigue, a lot of your cells start to go into this protective or defensive mode where it's going into the easiest way to describe it is hibernation. A lot
of my audience will actually already be familiar with me talking about this from Robert Naviaux's research, talking about the cell danger response.
Awesome.
Yeah, it sounds like you're familiar with that. So, so probably a lot of people listening already kind of are somewhat familiar with that idea that mitochondria kind of switch off energy production and go into danger response mode.
Right. Okay. Cool. So, so what ends up? To make a long story short, in this particular situation, a number of different things happen because the cells go into this this low energy state, or this hibernation. It's not producing a lot of energy, and in response to that, the cell continues to have a low level of energy demand, but it's not producing enough energy to meet that. So what ends up happening is your body shifts focus to something called the adenylate kinase reaction. So I don't want to get too technical in terms of the biochemistry here, but when we're talking about energy in the body, we're really talking about ATP, or an adenosine molecule with 3 phosphates. And when we use that energy molecule, the body essentially just breaks off that 3rd phosphate and you end up with ADP. Well, because the body is not able to produce as much ATP to meet its demand, after a period of time, it goes through what we call the adenylate kinase reaction, where it takes 2 ADP, combines them together, so you end up with an ATP, which is great because now you can use that ATP to produce energy, but it ends up with an AMP, and that AMP, or the adenosine monophosphate, is a compound that is not welcome in the cell. So what ends up happening is your cell wants to eliminate that, and so it does that. And the problem with that is over time, you're essentially reducing the energy pool. So when you start these individuals, you can take the D-ribose, you can take the CoQ10, you can take other things, but you're really not increasing the energy pool. So you might have a very short-term boost in energy levels, but long-term, you're really not correcting that underlying energy capacity deficiency. So that's one of the reasons why it will take a while for these individuals to kind of bring their bodies back out of that hibernation stage where those cells are starting to produce energy the way they should.
Mm-hmm. So when somebody has dysfunctional mitochondria, whether they have, and this is linked, we didn't really get into all the details here because we don't have time, but this is all, dysfunctional mitochondria is also linked with a number of other different conditions, neurological diseases, diabetes. What else? You tell us what else.
Oh, yeah, like I said, and I cover a number of different degenerative diseases in my book. But let me tell you, when I was doing the research for this, it seemed like literally everything that I was coming across was linked in some way to dysfunctional mitochondria. And I could have researched for another decade.
Yeah.
But I had to draw the line in the sand at some point, say, I got to start writing something. But it's been linked to cardiovascular disease, Gulf War syndrome, immune disorders. Like I said, the list goes on and on. So one of the things that we're seeing is that at some point there is, for whatever reason, there is an insult to the mitochondria, and as I mentioned, it's drugs, mitochondrial toxins or environmental pollutants, a mismatch in energy, or sorry, supply versus demand. For whatever reason, there's an insult to the mitochondria, and these mitochondria start to dysfunction. So depending on where those mitochondria that are insulted reside, that's where you start to see those presentations. So if the mitochondria...
That was going to be my next question, is if it's just sort of mitochondrial dysfunction underlies so many different diseases, what determines like whether it manifests, that mitochondrial damage and dysfunction manifests as one disease versus another?
Yeah. Well, first of all, in general, if you have mitochondrial damage, your overall health is going to be impacted. And that's one of the reasons why if you have cardiovascular disease, which has strongly been linked to dysfunctional mitochondria, you're at increased risk of neurological conditions like Alzheimer's, because the mechanism is the same. You have mitochondrial damage in the heart, you're likely going to have it in the brain as well. But it gets a little more nuanced than that, because one of the things that happens from the time we're conceived, in our mother's womb, as we age, these mitochondria have the DNA gets split between different cells. So some mitochondria that have more DNA damage might end up being concentrated in one organ versus the other. So the threshold for damage differs between organ to organ. So even though overall you're looking at minimizing mitochondrial dysfunction, some organs might have inherently a lower threshold. So when we expose our bodies to certain toxins, those mitochondria that are healthy, that might reside in the muscles, won't be impacted to a great extent. But maybe over time, the mitochondria that had a lower threshold for damage eventually got segregated into the heart. So the heart's going to be the first one to experience damage upon insult. So, and this is one thing that I learned in researching mitochondrial disease, which is an inherited condition. And one of the reasons why we see such a wide variance between individuals with mitochondrial disease is that as we age, those dysfunctional mitochondria, the ones that have a little bit more damage than others, really kind of get thrown in different organs, and that's what leads to these different presentations.
Mm-hmm. Excellent. So we basically at this point we know why mitochondria are so important, and we know that damage and dysfunction in mitochondria is linked with all sorts of different diseases, almost every disease, chronic disease imaginable, and fatigue in particular. And we know that this is also linked with aging itself. And we also know that damaged and dysfunctional mitochondria are extremely common in people, after the age of 40 or so. So having said that probably lots of people listening to this podcast have dysfunctional mitochondria. Let's talk about some of the things that can be done from a practical perspective that people can start doing to improve their mitochondrial health. Sure.
Yeah. So one of the things I always start off with is, living a clean lifestyle. It's probably one of the easier things to do. So if you have access to and can afford it, I highly recommend an organic diet. As I mentioned, there are a number of studies now showing different pesticides have a significant detrimental impact to mitochondria. Eliminating all the artificial junk in our diet would also help. There was a study that showed, in particular, this one artificial blue color had a negative impact to mitochondria. Thankfully, in North America, that particular blue color is banned, but it's still used in large quantities in other parts of the world, where it's you can find it in candy, you can find it in those. The shave gels. For some reason they're always colored blue. I'm not too sure why. But these are the sources of that particular blue color. So and then there are other situations or other toxins that are a little bit more difficult to avoid. So as an example, particulate matter, or something called PM10, or fine air pollution particulate matter and air pollution, that has also been shown to have a negative impact to mitochondria, although depending on where you live, it might not be as easy to kind of avoid that. But in general, live a clean lifestyle. Then the next thing, and this is probably the biggest take-home message that I always mention whenever I talk about mitochondria, is physical activity. And if I can kind of send everyone home with one message, being physically active is probably the greatest thing you can do for mitochondria health. Not only is being physically active allowing you to use up that energy that your body creates, so that you're not creating this backlog of energy and creating free radicals, but in that process, you actually build capacity. So what I mean is that when you create this demand for energy, what ends up happening is that the body thinks, oh, well, you know what? I don't have enough energy to meet this demand. So what it does is its mitochondria start to divide. And again, more mitochondria you have, the more energy it can produce. The benefit to that is that the next time you go out and exercise, you now have that workload being shared amongst a greater number of mitochondria. So each individual mitochondria is under less metabolic stress and spilling less free radicals. What that also means, though, is that at rest, which is the vast majority of our life, even for an elite athlete, you know, you look at 24 hours of their day, they're still probably at rest the majority of the time. During that time, there are far fewer free radicals being generated. So, you know, you take that over a course of a lifetime, you're really minimizing the free radical damage that happens within the mitochondria.
And there's a few things I want to dig into here. So one, first of all, you're saying that it minimizes mitochondrial damage, mitochondrial free radical production, I would imagine, at rest. Now, what's the mechanism behind that? The mitochondria grow bigger and stronger in response to exercise. And then how does that translate into less free radical production?
Right. So, and I'm simplifying here, but the easiest way to describe it is workload on a particular mitochondria. So so the number of free radicals generated is closely linked to the metabolic demands placed on that mitochondria. So if there are a few mitochondria in a cell and there's a high workload or a demand, each mitochondria is under considerable stress, and that is going to spill, that stress is going to manifest as free radicals being spilled and damaging the mitochondria. When your mitochondria start to divide, and we call that mitochondrial biogenesis, or creating more mitochondria, and you go out and do that same workload, now you have, say, double the number of mitochondria, and the stress that each individual mitochondria is under is now halved. So the number of free radicals generated is going to be far less. But at the same time, and I mentioned that was a bit of a simplification. When we do exercise, and exercise is a highly oxidative state, we are actually generating free radicals. And going back to what we said before, often those free radicals have to be put into context. And when we exercise, those free radicals are actually not a bad thing. And that's because our body takes those free radicals that are generated during physical activity, puts it into context of not enough energy being produced, even though there are free radicals, and goes about certain adaptive responses that allow our bodies to get stronger. So one of those is upregulating certain genes, and one of the ones that seem to also be quite popular in the scientific community, or at least that's being talked about a lot, is NRF2. And that is a gene that's switched on in the presence of free radicals, again, within a certain context, and allow our bodies to naturally produce what we call our primary antioxidants. So not the antioxidants that we get from our food, but these are the antioxidants that are generated within our body. And these are the most important ones, because these can actually target those free radicals generated within the mitochondria. And that's one of the challenges with any antioxidant that that exist in nutritional supplement industry, or even the ones that are being researched and manufactured at the pharmaceutical level, is it's incredibly difficult to target those antioxidants to not only the mitochondria, but to the matrix, the inner portion of the mitochondria. But by activating NRF2, we're actually able to generate those those antioxidants, in the immediate space where they're actually needed.
Yeah, beautiful. So what you're saying is hormesis, transient metabolic stressors like exercise being a good example of that, as well as certain phytonutrients also have that effect.
Yes.
Are actually creating these benefits through being free radicals. And they stimulate this endogenous, inside the mitochondria antioxidant response, and that is really the key to preventing damage and aging. One other thing I want to just add to this as a cool little layer that also goes back to what we were talking about before, is linking this with antioxidant supplementation. There's actually research done by a German researcher named Michael Risto, who has actually done trials using antioxidant supplementation before and after exercise, which used to be commonly advised, right? We used to think free radicals are bad, and we know exercise produces lots of free radicals, so make sure to take your antioxidants before and after exercise so you get the benefits of exercise without all the damage from the free radicals. Well, what these trials have found, and this has been replicated multiple times now, is that taking antioxidants around exercise actually blocks the body from getting the benefits of exercise. It blocks all of these hormetic signaling effects that you've mentioned. It's blocking these effects. So as you said, basically those free radicals are not just the bad guys, they're actually necessary to create these benefits.
Absolutely. And I'll go even further and mention that there are studies that show that timing of antioxidants is also important. So one of the things that has been shown in human clinical trials is that when you take antioxidants during the training phase, you actually block the improvements, or the improvements in body performance by training. Essentially, as you mentioned, you're blocking the signal that causes our bodies to adapt and become stronger, which is the whole point of training. Now, mind you, it's also been shown that you can, if you take antioxidants during the competition phase, so not necessarily during the training, because you really want to get those adaptive responses during training, but when you take antioxidants during the competition phase, it might extend your endurance and things like that. But you definitely want to make sure that the antioxidants that you take are timed with respect to the phase of your physical activity. So if you're training for a competition, by all means take antioxidants during that competition. But the lead up, the training phase, you want to get the maximum benefit out of your training, and that's where the antioxidants might not necessarily be the best time, the best time to take it.
Yeah, so for athletes, relevant, but for probably the average Joe, like looking to improve their health, who doesn't do any sort of competition, basically, I would say probably never use antioxidants around the exercise periods.
Right. Yeah. Yeah. You really want to be able to take advantage of those beneficial free radicals.
Yeah. So one thing that we would be remiss if we didn't mention, I know we're running out of time here, but chronic fatigue syndrome. Obviously, people with full-blown chronic fatigue syndrome, fibromyalgia, have a horrible time exercising. What are your recommendations there?
I think, well, first, you have to stay within your means. So you don't want to, all of a sudden go out and undertake intense physical activity, because essentially what you're going to do is the opposite effect of what you're trying to achieve. You're going to deplete the body. The body's going to go into it's further going to go into this hibernation phase. And slow even its energy production down even more. So the idea with this is to take it very slow. So you want to, just slowly increase your everyday physical activity. So as an example, instead of parking right in front of the door to the mall, you might want to park a little bit further. So things like just walking, gentle walking. The idea is to continue to do physical activity because you want to get the benefit of physical activity, but you don't want to exert yourself so much that you have the opposite response. So my recommendation would be to go slow and increase physical activity as your body adjusts and allows.
Yeah, and stay pretty far below the threshold that would trigger negative reactions and exhaustion for days. Like,
absolutely,
and start working there. Be familiarize yourself with that threshold, and kind of work from there with making sure not to overdo it.
Absolutely, that's right.
So what else? And I'm going to ask you I know we're almost out of time. So whatever time you have left that you're willing to spend with me, is there a few other things that you could mention as being beneficial for mitochondrial health? And if you have to run in 30 seconds, I totally understand. I would love to interview you in this class, but however many minutes you want to give.
Well, I'll quickly mention a few nutrients, and I won't go into detail. A lot of the details are in my book, but everything that happens in our body requires nutrients, and the mitochondria is no different. So when we look at what we call mitochondrial nutrients, so things like D-ribose would be incredibly important, because ribose is the backbone of that adenosine molecule that makes up ATP. Magnesium is also important. Magnesium is probably one of the most underrated minerals, and most people are deficient in it. What's interesting is, even though we talk about ATP as ATP, it really is what we call magnesium ATP. So that phosphate tail of ATP is actually stabilized by an ion of magnesium. So without magnesium, our bodies are not able to have the energy that it needs. We briefly talked about coenzyme Q10 or CoQ10. A critical component of the electron transport chain. And the older we get, this molecule or this nutrient becomes more vitamin-like. So essentially, supplementing becomes more important as we age. All sorts of different B vitamins are incredibly important. So one that sticks out in my mind as being particularly important is B3, which is the precursor to NAD+. And then there are a number of different phytochemicals from different herbs and foods that we eat that have a benefit to mitochondria. One thing that seems to be quite interesting is dark chocolate. I know chocolate in general has had a negative reputation for a very long time, but we're starting to see how beneficial the different compounds in chocolate are to overall health, but one in particular, and I talk about this a little bit in my book, is PQQ. Chocolate seems to be by far the greatest source of PQQ in the human diet, and this has an incredible benefit to the mitochondria. So there are a number of different things, but again, with respect to supplementation, I think that's always secondary to physical activity and making sure that you're not damaging your mitochondria any further from exposure to a number of toxins.
Beautiful. Well, Dr. No, thank you so much. It's been such a pleasure. I would love to have you on for 3 more hours. As I mentioned to you via email, and you were like, I can only swing an hour and barely make it at that time. So I appreciate you being flexible with your schedule and making
my pleasure. This was awesome.
Like I said, I would love to have you on again sometime, and maybe if we can make that happen, it would be a blast.
Let's make it happen.
Awesome, man. So for everyone listening, I highly, highly recommend that you go on Amazon and get Dr. No's book. It's called Mitochondria and the Future of Medicine, and it's being published on February 28th. I've already had an advance copy given to me. Excuse me there. Got people, my next interview calling me. So I've already had an advance copy given to me that I've had the pleasure of reading, and it's phenomenal. So highly, highly recommend everybody go get that book as soon as possible. It's also, you've done an amazing job of explaining all of this complex science in very simple terms, which I applaud you for. I think is incredible. Thank you again, and can't wait to have you on again.
My pleasure. Thanks, Ari.